for the introduction, and thanks. I would like to thank the organizers for the invitation.
Yeah, maybe I just switch.
Hi.
And we can hear you better. Yeah.
Okay.
Yeah.
So the title of my talk is Enumeration of non-archimedean curves in higher dimensional log Calabi-Yau varieties. It's joint work with Shankil. It originates from my thesis problem suggested by Maxine. And here is the plan of my talk. Start with background, then I describe our setup, then I explain the counting associated to extended spans. I'll explain what are they, and then tail conditions. And in the last part, I will introduce a new notion called skeletal curves, which play an essential role in the theory. So I start with background. When we have maximal degeneration of Calabi-Yau varieties, we obtain conjecturally SYZ torus vibration. Like this, at some base. And we have the torus vibration over the base with singular fibers. And we are interested in the enumeration of holomorphic curves with boundaries on torus fibers. So, for example, holomorphic disks with boundaries on one torus fiber, or holomorphic cylinders with boundary on two fibers, or holomorphic pair of cans, and more generally. So, these enumeration are expected to exhibit rich geometric properties such as wall crossing, associativity, canonical basis, etc. So there is a difficulty in the picture is that the counts of these red curves are not well defined invariants. Actually, they depend on various choices. So, since my thesis, I had been exploring a more algebraic approach. For the counts via non-Archimedean geometry. More precisely, via the theory of Berkovich spaces. So today I will explain you the enumeration in the case. Today I will explain the case of affine log Calabi-Yau varieties containing an open algebraic torus. So this case generalizes the two-dimensional log Calabi-Yau case that I work worked on before. And moreover, this case includes cluster varieties. Includes cluster varieties arising from representation theory. And another good feature about this case, instead of a completely general case, is that the construction is very explicit and also computable. So let me describe the setup of our case. Here is the setup. We start with U, connected, smooth, affine variety defined over complex numbers with a nowhere vanishing volume form. Omega, that's the nowhere vanishing volume form. And we assume that U containing an open algebraic torus that we denote by Tm. It's just M cancel with C star, where M is a z-dimensional lattice. So the thing we start is very simple. Just connected smooth affine variety over complex numbers together with the nowhere vanishing volume form, and we assume that the variety contains an open algebraic torus.
In volume form is standard one.
Sorry?
In volume form restricted to torus is a standard one.
Yes. Yes. So automatically it's yeah. So
it's not automatically because it could be monomial multiplied by standard.
Yes. Let's assume it's. I think I don't really need that.
Then it would be not block Calabi-Yau.
So let me assume that its volume form on the torus is standard one. Thank you. So.
When you say approach by a non-archimedean geometry of the space, what is the difference between that and like the Toric property?
It's two different geometry. One is like algebraic geometry. Tropical geometry is something different. You will see many tropical objects that I will use to help here. Yeah. So yes. So in order to pass from complex geometry to non-Archimedean geometry, we introduce the following notation. Let K be a field of Laurent power series, and we denote by superscript Ka. Just make base change from complex numbers to K, and then take analytification. So just like base change and take analytification. So for example, for our U, we can consider UKA, and also for our torus, we can consider the torus Ka. So they are analytic space. Now we consider C to be P1, analytic P1, minus some open disks. Our curve to be analytic P1 minus some open disks. So, for example, a pair of pens. Sorry? K is the field, base field. So we consider for P1 minus some open disks. For example, a pair of pens is just a P1 minus 3 disks. And a map from this curve to our U, UKA. And assume that we have more than 2 boundary components. Then we can consider skeleton CS inside C, which is just a convex hull of all the boundary points in C. Here's the picture. So actually, in terms of Berkovich spaces, this pair of pens looks like an infinite tree. This is our C, and it has 3 boundary points, 1, 2, 3. So when I take a convex hull of the 3 boundary points, I get this thing called a skeleton. So for
So this one is like tropical.
Yeah, this conference about other skeleton. Yeah.
No, I mean, it's not entirely the other one.
Yeah, it's materialized inside the Lagrangian arrays. It's kind of working. It's retracts. Yes.
yeah, so tropical thing will come a little bit later.
But in what sense is this one not a tropical?
I think it's just about the word tropical. So, but this is a good object. So for F sufficiently general, we have F of the skeleton lives inside the torus. Then we can composing with the valuation map tau from the torus to MR. So usually people call this tropicalization map just from analytification of algebraic torus to this R to the power D by taking valuation, coordinate-wise valuation, and called tropicalization map. So by composing with this valuation map, we get a map from the skeleton, this CS to MR. And one can, so the map looks like this. So this is MR. MR just the M tensor product with R, just the R to the power D. So we can show that the map from the skeleton to MR looks something like that. It's piecewise linear.
What is sufficient? What is the meaning of sufficiently general? What is the meaning of sufficiently general?
It's just for a very general F. I mean, we have modular space of F. For I will make it precise later.
Kind of difficult. Not enough.
Or complement to some non-dense
Yeah.
space.
So this is piecewise linear. And we call it the spine associated to F. So now I just explained that when we have any such map from curve to our U, I get some spine, and our goal is that if we are given any spine, a span S. In other words, a piecewise linear map from a tree to MR. We want to count the number of non-Archimedean holomorphic curves in this U, whose associated span is S. So I explained from curve we get span, and now given span we want to count how many curves are there.
No rationality condition on the map, or
Sorry?
no rationality condition.
A tree.
Purpose.
Yeah.
Rational.
Yeah. Rational.
Okay.
And do you expect these things always defined to have some walls when you?
Yes. So I will. Yeah. I have to put some transversality condition on the span. So just let me mention that we also have to fix some homology class, but I omit in the talk. So
and the count of the number of actual maps,
yes.
not non-Archimedean.
Not actual number of non-Archimedean curves.
No, but it's like count of actual holomorphic, not non-Archimedean.
You can use Gaga, for example, to relate. They are all the same. Yes. The first difficulty that we have is that if we consider the modular space of all such holomorphic curves, then this modular space is infinite dimensional, because we can vary infinitely many coefficients of the map F without changing this combinatoric spine. So our strategy is the following. Which is a variant of the strategy in the two-dimensional case I worked on before, but actually it's more general and more conceptual, and finally it simplifies many things. So first we have to take compactification U in Y such that the divisor Y minus U is SNC.
Sorry, what is non-Archimedean holomorphic curve?
It's a map from.
Map from this P1 minus some disks to U.
Why it is holomorphic?
Analytic.
Yeah, analytic. Given by power series. So
there is no Cauchy-Riemann equation.
No, it's algebra. It's kind of algebraic geometry in a sense.
algebraic.
It's rather estimate of the norms of coefficient.
Yeah. So first we take SNC compactification, and we don't need to assume that the compactification is minimal model. So minimal model not required, because we know that otherwise maybe we cannot get SNC. So second, we establish the counting of closed rational curves in Y in YKA with given extended span. MR.
So just want to interrupt. You will never use stable maps at all, or just strategy?
I only need to use a little bit.
Yeah, okay.
Third, we impose Toric tail conditions. And using Toric tail conditions, we relate the closed curve counting above to open curve counting. And finally, we introduce a new notion of skeletal curves. And this gives us further understanding of the underlying modular space.
So is the answer going to be something different than usual Minkowskian multiplicity?
You cannot just read out from the tropical curve the counts, because it's not toric geometry here. So now let me explain let me explain our strategy in more detail.
So if you had asked this question in the toric case, then the answer would be Minkowskian multiplicity?
Yeah, then it's trivial, the counts. Not trivial doesn't mean it's always zero. It's just you don't get interested in this thing because we are interested in this kind of singularities, these singular fibers. So we fix a spine S in MR with n ends. So as Maxime already pointed out, we also assume some genericity condition in this some genericity condition on the spine roughly means that the spine should be transverse to walls, but I don't have enough time to define walls here. Let's just think that the spines are sufficiently generic.
So I don't hear the goal is to give the number depending only on the map 3 to
Yes.
So your goal is can only possibly depend on the tropical curve if you succeed with the answer.
No, it depends also on you.
So you fix you and then
Sure. Yeah. So let's say we are given a span S like this. So first we just extend the ends straight to infinity, and we obtain something like this. Just extend all the ends straight to infinity, we denote by S hat, and we call it extended spine. S hat in MR. So now our first aim is to count closed rational curves in YKA with extended spine S hat. I mean, when we have rational curves, we just take the same convex hull of the marked points, and we get spine. We get extended spine. We want it to be this S hat.
So this extension of the ends to the to infinity is the same as transverse to 1. So,
No,
Walls has some dimension 1 stuff.
so what does it mean by string?
extend just because this is Rn,
It's flat
and
space.
we know what it does straight mean. This is Rn, and we have array, we just extend. So we want to count this, and in order to get the right dimension of the modular space, we have to add an auxiliary marked point. We add an auxiliary marked point. Otherwise, the modular space is not of good dimension, cannot count. Auxiliary marked point to S hat, and we obtain what the so-called extended N1 span. S hat prime, just span with n infinite ends and with an extra marked point. And later we will use skeletal curves to show that it's independent of this auxiliary. So, in order to explain the count, let me introduce some notations. First, we have n infinite ends of our extended span S hat, and infinite ends of S hat. This gives us n vectors. P1 we denote by P1 to Pn inside M. Each end gives a direction. It's just a direction, but
It will be non-zero.
with also multiplicity.
It will be non-zero vectors. Yeah?
Non-zero vectors.
And not primitive. Yeah.
Not necessarily primitive. So now, by Toric blow-up, of our S and C compactification, Y, we can assume that Pi has divisorial center. Which I denote dpi inside D.
PI is a vector.
Pi is a point in M, and M is this lattice. So we can think of points in this lattice as divisorial valuations on this torus. So we denote by Mi the multiplicity of Pi. Just means that Pi is Mi times primitive vector, and we denote by big bold P just tuple, n tuple of the vectors.
What is a primitive vector?
Not divisible by any positive.
So this is just a simple notation. And then I introduce the modular space that we will use. So let M 0 and 1 SV YKA E with the notation is a bit complicated, but just in order for us to remember everything inside. Let this be the modular space of n plus 1 pointed rational stable mass F. So rational stable maps F from some nodal rational curve with n+1 marked points P1 to Pnq goes to yka of some curve class beta. We will ignore curve class for this talk, and we assume that it has a stable domain. So we assume that the domain is a stable pointed curve, and moreover, we assume that the pre-image of the boundary D is sum of MIPI. So it's nothing complicated. We just consider the subspace of stable maps such that the PIs go to the boundary such that the PIs go to the boundary with given multiplicities, and also we assume that the domain is stable. I should also assume that small pi goes to D, maybe such that this and small pi is mapped to the divisor dpi. This is all we need. So
And Q goes to the auxiliary.
and this is just the space of stable maps, and then we also denote by SP we denote by this the space of extended N1 spines in MR. So we just have a modular space of analytic maps and also a modular space of the tropical or just the spines. Okay. So now we consider commutative diagram from this space of analytic stable maps. It maps to the space of stable pointed stable curves times y. Just by taking we denote this map by phi. It is just take domain of the stable map and the evaluation of the last marked point. So consider domain of stable map and evaluation of last marked point. It maps to just the domain times the target. And if we take a span of every stable map here, we get a map from this space of stable maps to the space of spans. And on the level of spans, we can also take domain and the evaluation of last marked point that I denote by psi. That's the domain, evaluation of last marked point. And it goes to the tropical version of this. And trop, just the space of tropical curves times this. So here we have a tropicalization map pi. And we have our pointed spine S hat prime lives in here. So with these preparations, I can state the theorem for counting these extended ones. So theorem. There exists a dense Zariski open R0 inside this space M0 n plus aka times y, and an open connected neighborhood V of our pointed spine S hat prime in the space of all spines, such that first the projection of R0 to the first factor is surjective, and second, if I let R to be R0, R0, as you will see, this open Zariski dense open Zariski open R0, it's some nice region here, so that everything will be nice. So if I let R to be R0 intersect with the pre-image of pi of psi of V, and let N be the intersection of the pre-image by SP of V intersect with phi inverse of R. I will explain just in a minute. Then the restriction phi restricted to N, that goes from N to R. This is a finite Dao map. And so we can take degree of finite Dao map. Its degree, I just write here. Its degree gives the count that we want of rational curves associated to S hat prime. So we don't need a virtual fundamental class. It's just the finite map.
So it hits kind of cross ratio, yeah, and
yes,
and point in the target.
Yeah. So the domain, the cross ratio in the domain is fixed.
Yeah. And generic point could be everywhere. Yeah.
Yes. Yeah. So let me explain a little bit this N. It's a bit. If you read from Blackboard, maybe not easy to see, but it's very simple. It just means that it's just the subspace of this modular space of stable maps, such that the spine is in V, the spine is close to our spine, and as Maxime pointed out, and the modulus of the domain is given, and also where the last marked point goes is also given by this R. So when we restrict to this nice N, we get a finite Dao map, and the degree gives the count.
So it really doesn't depend on order of vanishing of volume form and divisors. It's strange. Yeah.
Order of vanishing.
Of order of, because volume form can have first order 4 or 0 some order.
Here you see that the points goes to DPI,
yeah,
and the DPI are the divisorial center of the PI.
So
and
it already has logarithmic.
divisors,
That's automatically logarithmic. Yeah.
yeah, these divisors are where the volume form has first order form. Yes, and another remark about this R0. So we choose this Zariski open R0 to have this finite Daoness. Otherwise, we would need a virtual fundamental class. But fortunately, we can get this Zariski open, means we shrink a little bit. Like, if the modulus and where the last marked point goes are sufficiently general, then the counts are just the naive counts. So
And what is topological space of spines? Yeah, it's not terribly obvious.
It's obvious in this Toric case because it's just in Rn. So it's
so you have finitely many intervals and you change
yeah,
sizes.
we just move every like affine piece in like affine way.
I see.
To rotate. Yes. So and another remark about the first condition is that we shrink a little bit to get this naive counts, but it's good enough in the sense that we are not missing any modulus of the domain, because later in the theory we have to vary modulus of the domain to make many proofs, and it's important that we don't miss anything here. Remark, maybe just another remark, is that theorem implies that the count is also invariant under a small deformation of our spine. So formula, you need this theorem just gives the count, but for formula you need more properties of the counts.
Yeah, but I found it surprising. It's the risky open because the question is kind of analytically.
Yeah, here we get the risky open because to get this, to prove this first, we show that the Zariski open actually exists on the level of algebraic geometry without AA. We get the Zariski open, and over which it's a Tau. But then we need to go to analytic geometry to show that it's proper. And we prove it's proper and a Tau, so it's finite.
I guess I asked you before, whatever the formula is it or will it not be a product of contributions from the
No, not at all, because there are singularities of projections. Yes.
Yeah, but those all happen at
Infinity, yeah, but I think
Not just the legs, because at infinity they are very complicated things that you don't see from Rn.
yeah, there are coefficients of certain polynomials which
I mean, all the complicated things, they sit somewhere like around this infinity, and you get all like wall crossing things in cluster algebra from this picture. Yeah, you go in, but for example, you go in and you have some multiplicity on the left, but you don't see what's there. You can, if the blow-ups are, or anyway, it's.
Do I just multiply by some possibly mysterious number that comes from there, or is there some sort of more complicated thing that you multiply by some
It's
unknowable number?
not just the number. You have to. I mean. The count finally can be obtained from wall crossing formulas. Okay, so now let me explain first part, tail conditions.
Are the space built so the WDV equation is automatically satisfied?
Here I don't know if it's related to WDV equations. So let me explain tail conditions. The idea is that we would like to relate the count here by the theorem of this extended span, the count of this extended span, and to the count of open curves associated to the original span. So for this we have to impose extra conditions on this extra tails that we add. So here is the picture. What we try to count originally is we are given some span, and we would like to count open curves that whose span is this given one. So the holomorphic curve may look like something like this. So here the span has 3 ends, and our curve has 3 boundary components. This is what we try to count. But we cannot count directly this. And what we do is that we add auxiliary tails to this curve, and we obtain a rational curve. Close the rational curve that looks like this. We add some tail, and the associated span is our extended span. So this we can count. The right-hand side we can count by the theorem. And the question is that does counting on the right-hand side, on the right, gives expected counting on the left. So, unfortunately, not necessarily, because the auxiliary tails that we add, they may do something terrible, irrelevant to this open curve. Let me just draw a picture. So we have our extended span. We have our span, and it is extended. And we may have a rational curve. So this is the thing we want to count. But when we add the tails may be something very bad. For example, the tails can do weird things. While the associated extended span is still the same one. So in order to avoid this bad tails, we just impose that each punctured tail, which means tail minus pi. So it's just the tail minus the marked point must stay in the torus Tm Ka. So this gives us, this extra condition gives us subspace that we call n tail inside n. And the next theorem we can show is that n tail inside n is a union of connected components. Here n is already analytic space. Yeah, but being union of connected components in Zariski topology or in analytic topology, they are the same notion. So next theorem we show that this analytic condition actually gives is both open and closed. Hence, if we restrict this map phi to n tail, we still have finite A dot. is still finitely down. And this gives expected count of open curves associated to the original span. So finally, let me spend the remaining minutes on the new notion of skeletal curves. So we recall that for any k non-Archimedean field and any x quasi-smooth k analytic space, if you don't know quasi-smooth, just smooth, with volume form phi. So then we have Temkin's theory of scalar semi-norm. It gives us an upper semi-continuous function, norm of phi, that goes from x to positive numbers. So this function was previously constructed also by Kontsevich Soberman, previously constructed by Kontsevich Soberman and Niguez Mustafa by divisorial relations. But Temkin's formulation, we have to use his theory for the proofs. So we have this upper semi-continuous function, and then we can define the subset of x sk x phi to be the maximal locus of this upper semi-continuous function. It's called the skeleton of x with respect to phi. And if we take union over all such phi, then it is called the essential skeleton of x. So now I can state the theorem. For any map f from some point in the nodal curve to yk analytic, such that the pre-image of the boundary is as before, and let C naught to be just the punctured curve. So we see that, maybe let me first finish the statement. Then f maps some point in the skeleton of C naught into the skeleton of U if and only if f maps the whole skeleton of C naught into the skeleton of U. So for such f, we call it skeletal curves. We refer to such curves as skeletal curves.
Oh, before x, you consider just it was important. It's not projective. It's could be open part of projective.
Yes.
It depends on the how it doesn't. It's not Baratian invariant story. Yes.
This x can be just
Open part.
our u.
Yeah.
Yeah.
And if you remove something, the skeleton will change. Yeah. If you remove some part from x, that takes the risky open. This
If I remove more things.
Yeah.
Yeah, then it may change.
Yeah, I see.
Yeah, for example, for this curve, if
Uh-huh.
I remove more points, the skeleton gets bigger.
Yeah.
Yeah. So the theorem says that if f maps some point in the skeleton of the curve into the skeleton of the log Calabi-Yau, then f must map the whole skeleton of the curve into skeleton of log Calabi-Yau. And if we have a curve whose skeleton lives in the skeleton of the ambient space, we call it a skeletal curve. So this skeletal curves has many important implications. So first, let's consider again our map. Oh, it was behind here. Let us consider again our map phi from the space of stable maps to the space of stable curves by taking modulus of domain and evaluation of last marked point. And inside the target, we have skeleton of the target. So the skeleton of the target is the tropical space. And inside this tropical space, we have graph of we consider graph G of our spine, extended spine S hat. So then we can show that phi inverse of G intersect with SP inverse of S hat inside phi inverse of G. This is a disjoint. This is a union of connected components, and each connected component is homomorphic to G. So it's quite surprising that for skeletal curves we can just slide the last marked point along the skeleton and get homomorphism. Phi becomes homomorphism from the skeleton to G. And this implies that the count is independent of the choice of the auxiliary marked point. So I don't have time. Let me just say orally that it has other implications. So the second implication is that we see that for skeletal curves, the associated spine is just a restriction of the map to the skeleton. So we no longer need to take some tropical projection. And this implies that our counts are actually independent of choice of the torus inside, and more generally, so in terms of independence, So in terms of cluster algebra, it means that the count is independent of choice of C, and in terms of SYZ vibration, it implies that the count is independent of choice of SYZ vibration. So it's really intrinsic to the variety. Without it doesn't see the model. It's intrinsic because skeleton is intrinsic to the in log Calabi-Yau variety. And the last implication of skeletal curve is that it plays important role in wall crossing, that we use skeletal curves to prove some properties of wall crossing that we don't know how to do it otherwise. And I explained it, maybe I will explain it in my future talks. Somehow the skeletal curves, they are the most generic curves in the modular space, and when we move it across the walls, it's easier to move. So thank you very much for your attention.
Questions? Marks? In fact, I have some questions. So in the skeleton you don't have canonical affine structure, but still there are walls there, yeah?
Yes.
Yeah, and the topology on space of skeletal curves, because you can break everywhere.
A topology on the space of skeletal curves.
Yeah.
But if the skeletal curves, they are generic enough, then the space of skeletal curves, it's homomorphic to the space of spines. It's like locally homomorphic to the space of spines.
So it's you choose kind of any cluster torus and.
But so if we choose any torus, we get a projection. Then we get this homomorphism to the space of spines.
I see.
But then we see that it's just we don't need to choose it because it lives, because this skeleton is intrinsic.
So you mentioned canonical basis at the beginning of your talk. What does it mean?
So to get a canonical basis, we count.
It's canonical basis of mirror rule, yeah.
Yes. So here I just explained, given a span, how to get a number. So in order to get canonical basis, we have to count specific spans. So, for example, it's I think you know it.
Maybe. So I have some picture of canonical basis, but it's like
so like for canonical basis, we count spans with two ends, and one end in some chamber, the other end going to infinity with some given direction.
Okay.
So the idea is that if you remove walls, you get the rest will be kind of canonically mapped to some small domains affine structures, and you can try to count intrinsically these things.
Yes, and to go across walls, we use skeletal curves as we use here. Here it's somehow moving the last marked point crossing a wall. So if we want to move the whole span across a wall, this also is very nice.
Okay. So this picture.